Hello everyone. Let's get started. In our last video, we discussed the Laplacian and uh, gradient of a scalar field and also divergence. Okay. In this video, we are going to extend our discussion for further. It is called divergence theorem, right? Okay. Before moving to the divergence theorem, so in our last discussion, the Laplacians we can write in this way, right? As similar to this notation, right? Okay, so how can we write that uh, Laplacian in that notation? Phi. So this is the scalar. We are going to differentiate with respect to vector two times, right? So this is the notation in the index notation we can use for this one, right? Okay, so this also index notations, but this is also another way of writing that one. This is some kind of a shorthand writing, right? Okay, right. Okay, so today we are going to start the divergence theorem. Okay, so one of the important theorem in mathematics, right? Vector calculus especially. So to understand this one, let me take one a differential element. It's a cubical differential element, uh, which has a dimension of, let's say, dx, dy, and dz. Okay, so this is your x, y, and z direction, right? Okay. Uh, I can take x1, x2, x3 also. Okay, no problem, right? So let's see, let me use x, y, z. Okay, right. So actually, x1, x2, x3, right? Uh, or else or else use x, y, z, right? Sorry, x1, x2, x3, right? Why do you want to confuse you? Why do I want to confuse you, right? x1, x2, and x3. This is dx1, dx2, and dx3, right? Okay. So now, uh, what I'm going to do, let's say the uh, let's say some flow it take place in this element, right? This flow, it's a three-dimension flow. Like let me take consider only the x direction flow, right? So let's say the flow is vector field is this direction, right? So that means this is our Vx, right? So that means V1. Okay. V1, that means velocity in this direction, right? Okay. Right. Uh, so then this side it's a inflow, the inflow in. Then similarly, you can take it this side is uh, uh, outlet, right? Inlet and outlet. So we are trying to calculate the the loss, right? Uh, okay, loss in the flow, right? Let's say something is happening inside, then some of the flow is lost inside, right? So because of this media, right? Okay. So what I'm going to do, let me, this is just here in the picture, just I have shown in one direction flow, but in real case, it is like a three dimension, right? So that means, let's say the velocity vector, before that, it has the density. This element has a density. Let me take that density is a function of x1, x2, x3, right? Okay, it's a function of x1, x2, x3. Its a density is depends on the position, right? Density also changing. Okay, so that's what I assume here, right? Okay. Uh, okay, right. So let me take the flow rate, right? Let's say I'll consider that it's a steady state flow, right? Steady uh, steady state flow, right? Steady state flow means, the velocity it's constant. That mean constant mean not depends on the position. So if I take the velocity at this point, it is v. It's the same as v uh, when the times goes, right? So that means velocity change with time we ignore, right? Similarly here, it's it is not a v the same velocity, it will be different velocity, but that velocity at this point it is not changing with time, right? So that is the meaning of steady state flow, right? So here I have taken steady state flow, uh, and let me take the velocity vector. Okay, so uh, it will be v1, right? So it is a function of x1, x2, x3, right? Okay. Okay, so then E1, right? Similarly, V2, it is also depends on the position, right? X1, X2, X3, right? E2. Um, okay, last V3, the component, right? Velocity component in each side, right? So this is also function of position, E3. Okay, so this is the velocity, right? So I can write simply V1, E1, V2, E2, V3, E3, right? So don't confuse with uh, the the normal vector component. This is V1 is a function of the position, right? So it is not like the normal V vector what we discussed. This is now the velocity, right? Okay, so that's what I have written the first sentence like this, right? To make you understandable. Okay, so now let's say this is I will take this phase is that mean the phase this direction is phase 1, so this is phase 2, right? So now I am going to find the that mean uh, uh, mass, the mass, right? The mass exciting exciting um, uh, let's say yeah, mass okay, I will write this way: mass, the mass input, right? Input. So that mean mass input mean I am trying to calculate at phase 1, right? So what is mass input at phase 1? So that mean here velocity is v1, right? Then you have to multiply the mean mass rate. So I can say yeah, I am calculating actually the rate, mass rate. Okay, I am calculating actually the rate. Okay. So this is something you remember, right? So that means flow rate into density, right? So that is something the mass rate, right? Per second, right? Okay, so that means flow rate is uh, uh, that means area of this one, right? Area of this phase, that is actually dx1 into dx3, right? So that is the area of this one, right? So what is Q? Q is actually area into velocity, right? Okay, right. So here Q. So actually I'm using the momentum law, right? Newton momentum law, right? The area is this one, the velocity is v1, right? Okay, then the density is rho. Okay, so this is that. Okay, I can write that one here, rho v1, uh, velocity is dx1, sorry, area is dx3, right? Okay, so this is your input, right? Similarly, I will calculate the mass. Okay, the mass exciting through phase 2, right? So now if I calculate mass exciting through phase, so now I have to calculate the velocity here, right? What is the velocity here? How can I calculate this velocity? I cannot take the same velocity here because velocity is changing, right? So this is what we discussed the Taylor series uh, in our video number 16, right? 16 or 17, right? Okay. Okay. The previous video we discussed, right? So let me write that one, right? So that means what is the Taylor series we discussed? If you know the velocity, the function value at one point, you can estimate the function value at another point using the Taylor series, right? Okay. So what is Taylor series, right? Let me write let me erase this one first, right? We can write it later. First, try to calculate the velocity here, right? So that means Taylor series. So what is Taylor series we discussed, right? So let me write the Taylor series again, f of x. Okay. Then here, f of, okay, I will write that the Taylor series we'll discuss here, f of a, then x minus a, f dash, that means f first derivative of a, then x minus a squared over 2 f second derivative of a. So like that it continue, right? Okay. So now here you think about this way, right? This is my point. That means it is actually I'm considering the point along this point, right? So that means at the midpoint of the face, right? So this is my point A. So in this case, my A, I'll take x1 direction. A is my x1, right? Okay, right. So now here, I'm going to estimate the value at this point, right? So this is what is this point? A plus dx1, right? Okay. So in other word, uh, so this is x1, right? Okay. So in other word, okay, I will write this one A equal x1, right? So that means this one x1 plus dx1, right? Okay. Right. So therefore, this is my x, right? So this is actually my x, right? That means the x, the point where I have to estimate, right? This is my x. So therefore, x here, x1 plus dx1, right? So therefore, I have x minus a here, x minus a. So what is x minus a? It's actually dx1, right? Okay, right. So now I'm going to use the Taylor series, right? So to find the value of v1 at this point, right? At x. Okay, so let me v1 at x. Okay, so here I am finding the values, right? Okay, because v1 actually the vector, here I am finding the component, the value, right? These values, right? Okay, so v1, this value, right? So this value I am calculating, right? Okay, so v1, now I'm going to use the finite Taylor series, right? So here, first one, the value at our approximate point. In that point, we know the value is v1, right? Okay, plus. So now x minus a, we know dx1. So first I will write this one, right? So this is what is that f dash a? That means uh, differentiation, right? So it's a partial differentiation, right? So this one f dash, that is dou v1 over dou x1, right? Okay. So now I am taking one direction, right? Only x direction is change, I considered, right? Okay, so that is what I am using the one dimension case because I am calculating v1, right? Into dx1, right? Similarly, plus, if I use it again here, uh, second derivative, right? Dou 2v1 dou x1 squared, right? So it is into dx squared, right? Dx1. So like that, it will go, right? Okay. So now, again, here I am taking the very infinitesimal things. So therefore, the second order term, order of 2, I can ignore, right? Because already dx is the very small quantity, then dx squared even very small, right? So therefore, this part, so I can take it as 0, right? So that means as per the Taylor series, the value at the point where I'm considering at x, v1 plus v1 x1 dx1. Okay, so now this is the value at this point, right? Here, the value is v1x, right? So now I'm going to find the mass at that point, right? The mass exciting, right? Through 2, the second one, right? So again, the density when I multiply density, rho v1 plus, so dou v1 dou x1 dx1. This is the velocity, right? Velocity into density, right? Here density will come, right? So, okay, I will write with density, right? Rho density v1. Okay, yeah, here density will come, right? Okay, into the area dx2 dx3, right? dx2 dx3, right? Okay. Okay, previously the area is dx2 dx3, right? I have written dx1. That I am calculating this area, right? This is dx2 and dx3, right? Okay, there's a small typo here. Okay, right. Okay. So now what I'm going to do, I'm trying to calculate the uh, net flow. That means uh, mass loss, right? The loss of mass. The loss of mass uh, per unit time, right? Unit time in x1 direction, right? Okay. So that means now this is my output. This is my outflow. This is my outflow. This is my inlet, right? This is my input flow, right? Inlet. So that means outlet minus inlet. So that is my the loss, right? So therefore, when I output minus input, so this portion, right? This portion, this one cancel out, right? I will end up with the the remaining part, right? So therefore mass loss, I will end up only this one, right? I will write that one, dou rho v1 rho x1 dx1, right? Dx1, then dx2 dx3, right? When I this one also there, right? Dx2 dx3. Okay, right. So this is, I have considered only x1 direction, right? Similarly, I can consider all direction, right? Similarly, right? Similarly, if I consider all three direction, consider, right, uh, all three direction. So therefore, I can calculate the total loss, mass loss, right? Mass loss per unit time, right? So I will get the each direction one I have to calculate, right? The first one we calculate dou rho v1 rho x1 here dx. Okay, dx1 dx2 dx3, right? The same thing for second direction also come, right? Therefore I will take that part out of this bracket, right? So here you will get rho v2 rho x2 plus rho v3 dou x3, right? Into uh, dx1 dx2 dx3. Okay, what is this one? This is already we discussed, right? What is this one? This is something we discussed, right? If you write it now in the index notation, okay? Uh, so what is this actually? This is the dot product between your del operator, okay, and this vector function, right? So this is actually, what is this one? Something we studied, the divergence, right? Okay, so into this one, right? So what is this one? This is our divergence. This is something we discussed, right? There's a physical, this is the physical meaning of a divergence. What is actually the divergence? Divergence mean mass loss per one unit volume, right? So the total mass loss, this one into the volume, right? The volume of this one, right? Okay, right. So therefore, the mass loss per unit time for unit volume, right? Unit volume, actually, that is the divergence. Okay. So that means if divergence is positive, right? Let's say this is divergence of this one, right? This divergence of this one, if it is positive, that means mass loss, right? Mass loss is positive, right? Mass loss. Okay. Mass loss mean, what do you mean by mass loss? Mass loss in the sense, so that means your, uh, how can I say, that means spread out, right? That means mass, uh, uh, loss mean it's like mass in spread out, right? So that means is mass uh, what happens inside. You can see here mass loss mean actually the something is coming in then going out, some of the mass it is inside here. So therefore the element is volume of the element is increased, right? This volume. Okay, so that means spread out. If it is another case, that means divergence is negative, right? Divergence is negative. Rho v is negative. This is spread out, right? Spread out case, right? So in this case, mass gain, right? So that means mass increase. So when it is coming out, the outlet has taken something inside the element and it's coming that one also. That means the element volume is decreased, right? So that is this case. This case called the convergent, right? Okay, I think convergent, the point. Yeah, it's called converge. Okay, right. So these are the two things happening, right? Okay, so now consider this one, right? Consider a case. Let's say one surface, right? Three-dimension surface. So what is actually divergent? Divergence now we understood at one point if you calculate the divergence because unit volume, right? Now volume less, 1 point now we are calculating divergence. So it is giving what is the amount of mass it is coming out, right? From that, whether it is shrinking or spread out. Okay, divergence is positive. That is what happening here, right? So for example, if our surface, previously we consider one element, right? That means the cubical element, infinitesimal. Now I'm considering like any arbitrary volume, right? So if I want to calculate the total mass loss for this one, for this volume, now let's say volume V. Okay, so V is volume, right? Not velocity. So now the total mass loss. So per unit, this is the value, right? This is per 1 unit volume. So I'm calculating per unit time, right? Okay. So now if I want to calculate for entire volume, I have to integrate, right? So this is the volume integrate, right? Integration is volume. If I want to convert into the Cartesian coordinate, it will be triple integration, right? So it will be triple integration. Okay. Okay. Uh, dV. Okay. So this is volume, capital V, right? Okay. So now what is happening here? Let's think about this one, right? Let me uh, divide this one into small element, right? Okay, or else let me draw a solid line. Okay. Right. So what is happening here? Each point you are calculating the mass loss, right? From the divergence, applying the divergence. Each point you are calculating this one, right? Okay, so each point you are calculating this one. You see, if you take two different points, right? So let's say this point and this point, right? Here I will I will draw it separately. So this one point, this is the divergent. The next point you are calculating here, right? So what happened? These two is cancel out, right? Okay. So finally, one, that means opposite direction one, it's cancel out. Finally, only remains the outlets along these boundaries, right? So that is the net uh, mass loss on this uh, volume, right? So therefore, this will be equal to the mass loss uh, along this boundary, right? So that means this total mass loss, this volume integral of this one, right? The divergence of this one, dV, it is actually, so what is this one? You will get the how can I say, uh, that mean uh, the flow through boundary S, right? Let's say this boundary is S. Okay, boundary S. So how can I find this flow through this boundary, right? So let me bring again the same volume here. Okay. So now if I want to find the flow rate through this boundary, right? This surface has the normal vector is n. Okay. So now if I want to find the total mass coming out of this one, the net mass, right? The net mass, the net flow coming out of this one, that is the total loss, right? Okay, so how can I find that one? So it has the different, that means flow rate in one direction. I want to find the flow, it's coming along this normal direction of the surface, right? So how can I find the normal direction of the surface? Okay, so let's say I want to make the component flow rate along this direction, then I have small surface area. Let's say that surface area is ds. If I want to find the flow along this direction, right? You know the mass rate, right? That is uh, density into velocity, right? So this is my uh, uh, the vector, right? That means mass rate now. Now this mass rate I have to find along this direction, right? If I want to find one vector decompose into another vector, we discuss dot product, right? So now what I have done, this particular vector, I calculated along this direction. What is the component? It's something like directional derivative, right? So now this is now what is this velocity, right? The velocity into mass, the density. Now this one I have to multiply by area to calculate the total flow rate, right? ds. Okay. Now if I want to find the total flow rate, I have to integrate, right? Integrate along this boundary, right? That is called surface integral, right? So this is actually this one, right? Okay. This is something you studied as a divergent theorem, right? What is divergent theorem? The volume integral, okay? Volume integral, you are converting into surface integral, okay? ds. Okay, so now if we want to write this one into the index notation, right? Again, this direction, divergence is a scalar, right? So therefore, if you want to convert into uh, index notation, so how can you write the index notation? This one, okay. Let me write it in another direction, right? So therefore, finally, this is the divergent theorem we derive, right? So that means volume integral of divergence of, okay, divergence of, of a vector, right? Divergence of, right? So this one, right? Okay, divergence of a vector field, right? This is the vector, right? So therefore now that vector I can write it f, right? Okay, a function vector field. Divergence of vector field along the volume integral, it is equal surface integral of the same vector field dot product with normal vector along the surface into ds. Okay, so now if I want to write this one into uh, um, index notation, right? So this is vector field. If this is, I can write divergent, I can write like this, right? Fi comma I, right? dv. So now this is the scalar, right? Repeated index. Here, uh, surface integral Fi uh, dot ni, right? So that means Fi ni, right? Dot product, F1 N1, F2 N2, F3 N3, right? So summation conversion ds. Okay. So this is called divergence theorem, right? The divergence theorem. Okay. The same way, the divergence theorem, again, I'm saying f is now, the previously f is a vector, right? If f is a scalar function, then the same thing, instead of divergent, the same theorem we can write it like this, right? Volume integral. So now it will be like the gradient of f, right? Okay, gradient of f dv. This is, you can convert into surface integral, right? So this is surface integral, right? Okay, so into, now it will be f. This is just a scalar. This is vector now, ds, right? So you can use it for anything, right? Even the similarly, the divergent theorem use something you studied called curl theorem, right? The curl theorem, you consider the vertex, right, instead of the source. The same phenomena you can use to prove that one, right? I don't waste my time just giving the final this one, right? So that means same volume integral. Now curl means the cross product between del operator and the function, right? Now f is a vector now, right? So this is dv. Now surface integral of, now n, be careful, n cross f, right? Don't write it f cross n, right? N cross f into ds. Okay, so this is, you can write, right? Either you can write, this is called gradient theorem. So divergent theorem, gradient theorem, or curl theorem, right? So again, in all cases, the same approach, right? So I explained what is the physical meaning of divergent theorem also. Okay, I think, right. So this is the last video of our math preliminary for this lecture series, right? From the next lecture onwards, I'm going to start the fundamental of uh, continuum mechanics, right? I'm going to start the strain first. Well, what is strain? We are going to use our math preliminary what we have discussed so far. So therefore, please go through these videos and try to familiarize this one. I'll try to do some of the exercise, right? in one of the video before starting the strain concept, but my main focus is I will start the fundamental of continuum mechanics in next lecture series, right? Okay, again, if you don't subscribe my channel already, please subscribe and share with among your friends. Um, okay, see you on next video, right?